So this is now a continuation of the first part of the session. We took a quick break. So we're going to continue with on data representation. So based on the few questions that we received, one of the things I would like to address now is the idea of this binary representation of information. One other thing that you need to understand is how computers actually store this data. So we've talked about representing the data. We said computers basically use electricity. So they have an electrical signal, which we then transform into digital numbers, zeros and ones. We can then use these zeros and ones to encode text. We can also use the zeros and ones to encode images, and we can use the zeros and ones to encode sound. So this is how you should understand it. So the zeros and ones are just a representation. This is the electrical signal that the computer uses. This is the notation that the computer stores information in, and this is what it is used to represent text, images, or sound. So all data elements are made up of one of these. So these are all data elements. So the idea now is if we represent data as a sequence of binary values of zeros and ones, how do we store data in a computer? How do we store data? Well, there are multiple technologies that we can use to store data. The first type of technology is magnetic. Then we have electric. And then we have optic. So I'll give you examples of these of two. We will talk about magnetic and optics. And then in our next lecture, digital electronics, we will talk about the electric model. So let's start with the magnets. So what is a magnet and how does a magnet? So a magnet is essentially an element that you can find in the real world. If you find it in the form of a bar, its nature is if you bring two magnets together, they will either attract or they will repel each other. So the nature of a magnet is as follows. The magnet has something called a north pole and a south pole. Energy leaves the north pole and cycles back and enters into the south pole. So this we call the magnetic flux, the direction of its energy, the direction the energy actually moves. So this is how a magnet operates. So if I brought two magnets close to each other, and let's say their poles are facing opposite, in other words, this second magnet, the north pole is down, we flip the magnet and the south pole is up, what you will see is that the flux will change polarity. The magnetic flux will change polarity, it will change direction. So now it's traveling upwards. So there are two directions of travel. For this magnet, this guy, the direction of travel is downwards. Here, this guy, the direction of travel is upwards. Does this make sense? Right. So the reason why the magnets actually attract each other or repel each other, depending on how you bring them, if they say opposites attract, right? So if you notice, what happens if I have flux going in a downward direction and flux from another body going in an upward direction? Imagine you have two pipes of water and the water is gushing out of these two pipes and you face them opposite each other. What will happen is when they come close enough to each other and they're moving in the opposite direction, they will create a swirl. So that swirl is like a vortex, and this vortex sucks everything inwards. That's why the magnets now attract. Whereas if they're on the same side, it's as if you pointed the nozzles of your water tap directly opposite to each other. North with north, south with south. So what happens when they hit? They start to create pressure and they repel in the opposite direction. So what does this have to do with how computers store information? Well, given the natural properties of a magnet, Another thing that you need to know is if you have a magnet and you apply a strong electrical shock to that magnet, what will happen is it will invert polarity. If you shock it, you will invert the polarity. What is the polarity? The direction. Polarity is the direction of travel. So it can be downwards or it can be upwards. So if a magnet such as this, it's in the downwards direction and you apply a strong enough electric shock to it, it will flip. The North Pole will turn south and the South Pole will turn north. Then it will flip its direction of polarity. Does that make sense? We attach a strong electrical current, it will flip. So essentially, using these properties of a magnet, we can use the downwards notation to represent a 0 and the upward notation to represent a 1. I hope that makes sense. So in essence, if I have a file and the file is a 3 megabyte file, this MB means million and byte. We all know what million means. Byte means 8 bits. Each single bit from this guy, each single bit will be represented by one magnet, one magnetic dot. Each bit will be represented by a magnet dot. So if you look at your magnetic hard drives, your magnetic hard disk, they are made up of, they look like disks, they are round, and they have all these dots of magnetic material, very tiny dots, and each magnet can hold 1 bit of data. And if it's a magnet technology, if it's magnetic, we call it a disk with a K. Whereas if it's an optical disk that uses light, we call it, if it's an optical disk like Blu-ray, DVD, CD-ROM, we spell it disk with a C. So keep that in mind. With a K means magnetic technology, with a C means optic technology. Does that make sense to everybody? Can I get a quick thumbs up? All right. So let's discuss the optical technology. How does it work? It works based on the principle of light. So the magnetic technology works with magnets, magnetism, which has polarity, which we can invert. The optics uses the principles of light. So here's how it works. Let's say we have a light source. So that light source flashes a light and light travels in a straight line. If that light source hits a flat surface, what happens? The light reflects in one direction. So it reflects in one direction. Whereas if a beam of light traveling in a straight line hits a curved surface instead of a flat surface, what actually happens is it breaks, it scatters. So if you had some sort of equipment that could measure light, like a lens, then in the first example, in case A, the light reflects in one direction, which means the sensor here receives a high amount of light reflected back. Whereas in the second case, this case B, where the light hits a curved surface and scatters, what happens is the lens receives a low amount of reflected light back. So by measuring the amount of electricity or light in this case, you can determine whether you are going to designate a 1 or a 0 to the feedback. Does that make sense, people? So I can use the reflective property of light to encode a 0 or a 1. So on the optical disc here, how does that actually work? Inside the optical disc, there's a special material that is like candle wax. It's called lacquer. So this lacquer material, if you heat it up, imagine it's just a piece of candle wax. So if this is a piece of candle wax in a bowl, if you heat it up, what happens? It melts and the surface flattens. And if you've ever played with candle wax, if you melt it and you leave it to rest, it will then solidify, creating a flat surface. So candle wax, it freezes really quickly. You apply heat, it melts quickly. The minute you remove the heat, it solidifies very fast. So this lacquer material solidifies super fast. So if you apply a very strong amount of heat to this particular material, what happens is the surface begins to bubble, it begins to boil. So it creates a rough surface. And if you remove the heat energy immediately, it will solidify in this rough pattern. And when it solidifies in this rough pattern, what happens is if you now shine a light on this, it will reflect. If you shine a light on this, it will scatter in multiple directions. So you can now have a lens that will now pick up the reflected light and measure its quantity. So this is why we call burning things to a CD literally CD burning, because you're literally burning it. You're burning the lacquer that is sandwiched in between the plastic that makes up the CD drum. So the CD-ROM, whether it's a Blu-ray or it's a DVD or a regular CD-ROM, the technology is all similar. The difference between a typical CD and, say, a DVD or a Blu-ray is the number of layers of material that you can have. So a high-capacity Blu-ray disc is the same, but instead of one layer of lacquer, it has 2 or in some cases 3 layers of lacquer. And the light it uses is a special kind of light that can penetrate different layers. So it can use different light to penetrate different layers. So on the same amount of surface area, you can have ×3 the amount of data stored at the different layers. But it all works on reflective technology. Does that make sense to everybody? So this is how the technologies work. So in our optical disc, we basically burn that lacquer material to create a flat surface or a curved surface. And that's basically the lesson for today. So we're going to just quickly jump into our slides and then round up everything. So let me jump to our main computer, and then we consolidate all the information that we've been able to acquire today. So first thing I'm going to do is I'm going to show you a surface of a disk. Magnified. So we're going to magnify. We're going to see if we can find a picture of a magnified. So there it is. You can see magnified, what it looks like. So you have pits and dits. So these, and you can see how small they are. They're very tiny, just a few microns. So everywhere there's a dip, we can use that to encode a 0 or a 1 if we like. We can use it to encode a 0, and everywhere there's a flat surface, we can encode a 1. So what we're seeing here in this image, we can read it as 0, 0, 1, 0, 0, and so on. So there's a small space in between each data value. Does that make sense to everybody? Can I get a quick thumbs up if this is clear? We can also try to see or look for other pictures. Here's one that is a little bit clearer. So anywhere you have holes, so this is 0, 0, 0. And then anywhere there's a flat surface, it's basically a 1. So it's like Morse code. So that's how you burn certain areas, you make them flat, you make certain areas bumpy, and that is how the optical technology actually works. So if you're looking at this, we're looking at optical disc. If we're looking at a DVD disc, or let's say Blu-ray, Let's see if there's an image for that. So the Blu-ray will have multiple layers. I think this is what this guy is representing. So you can see the multiple layers, and each of these layers can be can reflect light at a specific frequency only. If it's not the frequency for that layer, the light can just pass through it. So I think that should make enough sense to everybody. So let's now take a look at our slides and finish up for today. So the concept of data representation discusses how computers store data inside their hardware. A human being, if they want to store data, one way they can do it is by using a pen and a paper. So we use the pen, which has ink, to stain the paper, and we draw out symbols or characters of the particular language we're using for our encoding process. So that is how a human being can store information. The human being will use the pen and paper to actually encode or transcribe a signal, transcribe a message using a set of characters. And from that set of characters can generate some type information. Is this clear to everybody? Can I get a quick thumbs up? So I think I'm having some difficulty on my second computer. So just give me a second. Let me try and re-log in. Just give me a minute, please. Just a minute. I need the two screens, otherwise I can't see your interactions in case somebody's trying to mention something. All right. So once again, everybody's clear? Data representation, how a computer captures and stores information for processing needs and for processing use. Right. So let's carry on. So if you take a look at the outline of the topics we're going to discuss, we looked at signals, digital and analog signals, and then we discussed a little bit of number base, and then we gave a little bit of background. We discussed the nature of how human beings see the world and how we can represent information about the real world in a computer. So while human beings fundamentally use sound, computers fundamentally use electricity. Human beings use sound to encode language, which they encode using a set of symbols, which is considered the alphabet of whatever language. For a computer, they typically use digital signals, digital specifically binary signals of zeros and ones. So if a human being wanted to represent information or store information in the real world, we can use a pen and a notebook, or we can use an etching tool where we can etch on wood, or we can etch on rock, or we can etch on bone, whatever the case may be. For a computer, they have to use natural elements. So some of the natural elements that we talked about is the use of magnets. So we can use magnets and electricity, and we can shock the magnet to change its polarity so that it can be, the polarity can be towards up or towards the bottom. So it can be facing up or down, which we can then use to encode a 0 or a 1. A computer can also use light to represent its information, where it can use a material called lacquer, and it can heat up that material till it makes it rough, makes the surface rough, or it makes the surface smooth. And it cools down and it solidifies and it retains its position. That is the nature of the lacquer material. So when I now shine a beam of light, a laser light, I can have a lens that collects the reflected light, and I can, in my computer, then can compare the amount of light that was transmitted versus the amount of light that was reflected back. So if the light reflected was a high value, it means I hit a flat surface. If it's a smaller value, it means I hit a curved surface and the light scattered, reducing its intensity. I can use that to encode a 0 or a 1. So that's how a computer can etch. The third technology was electricity. We didn't talk on electricity. We will discuss it when we look at the topic of logic gates. So that is the story so far. So the learning outcomes for this is you need to be able to compare and differentiate between analog and digital signals. You also need to explain how data is represented, stored, and manipulated inside a computer. So we've explained how data is represented. It's represented using binary values of zeros and ones. How is it stored? It can be stored differently in different types of technologies. There are fundamentally three main types. There's the magnetic technology, which we have magnetic disk spelled with a K. Then there's the optical technology, which is optical disk spelled with a C. And then you have the electric format, which uses logic gates, which is what we refer to today as the solid state drives. So the solid state drives actually make use of logic gate components. How are these data manipulated inside a computer? That we will again discuss next week when we look at logic gates. And after logic gates, we'll look at the topic of CPU and memory. So in the topic of CPU, we'll see how the CPU is made up of these logic gates and how these logic gates can manipulate electricity. And through the manipulation of electricity, how it can now come and generate new information from existing data. In other words, we'll see how the computer can use a transformation given by software instructions to change data into some type of result. And then lastly, you need to be able to perform some number conversion. So for the number conversion, you already expressed that you have mathematics for computing, and everybody is familiar with the basic number transformation. So you can transform a binary value to an octal value or to a decimal value or to a hexadecimal value. Correct, everybody? Can I get a quick thumbs up? Everybody's comfortable with number conversion. I don't need to spend time on it. All right, good. So here are a couple of key terms that you should be familiar with. I also gave you a document. Let me just open up the document real quick. I gave you a document that kind of summarizes the basics of data representation and how data is actually stored and manipulated inside the computer. It's about 6 pages. I need you to read this document before the next class. It's just a quick read, shouldn't take you more than 20 minutes. If there's anything you see in the document that you read you can't understand, remember, YouTube is your friend. If in case you're a visual type of learner, then you can use videos. You can find videos that will express or explain it in more subtle terms that will be more compatible, that will be more convenient for you. So when we talked about signals, we mentioned that signals are all basically analog, but we can use an analog signal and read it as if it's or read it in a digital form. So a digital signal is a way of reading an analog signals, which we mentioned by giving those brackets 5 volts to 10 volts or 15 volts to 20 volts. That will define whether we are encoding a 0 or a 1. So computers are finite machines, and because they're finite machines, they're very limited in the capability or their capacity to actually store data. So if you remember the problem of infinity, in the real world, there is just so much data and so much information that it is crazy to think you can represent it. Let me give you a very good example. I'll give this example. It's a story. It's a story of ancient China. So once upon a time, long, long ago, there was a Chinese emperor who wanted his subjects to make him a map of China so that he can see all his territory and he can monitor and he can plan. So the emperor said he wanted the map to be so detailed that he should be able to see every anthill on that map. So I want you to think about it. If you are going to build a map that is so detailed that it contains every house, every street, every river, and every anthill, that map is going to be super detailed. So the more super detailed the map is, the bigger the map is going to be. Does that make sense, people? The more detail I have in the map, the bigger the physical map is going to be. Correct? All right. So one of the cartographers of the emperor said to the emperor, if you want a map that is that detailed, then the map itself will be the size of China, which is going to be a problem. So you can't have the map of China as big as China because you want to capture every detail. And this is what would happen if you wanted to represent every information about the real world inside the computer. It's just too much. The real world, you will deal with the problem of infinity. So because of that problem of infinity, you have to abstract. That is why we said when you take the picture of an apple, all you can tell is maybe its shape, its size, its color. But you cannot tell the information about its texture, the information about its weight, the information about its taste. All of that is missing and gone. Does that make sense, people? So, analog signals are infinite. They contain too much information. So computers digitize the problem. When they digitize the problem, they digitize it and reduce its complexity. But in reducing its complexity, we lose a little bit of information, but it's okay because we only need enough information about a problem to actually perform computation. So if, let's say, for example, that example that I typically give, I have 3 friends and I have 6 oranges and I want to share it amongst them. Mathematically, I can represent that problem as 6 divided by 3. I don't need in my math to say 6 oranges. And I don't need in my math to say 3 people and the name of one is Muhammad, the other guy is Mark, and the other guy is John. I don't need to do that. I just need to represent 6 divided by 3. Very simple, very straightforward. So this is the purpose of using these digital signals. They're easier to deal with, they're easier to manipulate, and they are more convenient to you. So before we proceed, we're going to go online and we're going to Google analog versus digital signals to see some of the differences. So when I search for differences between analog and digital signals, I am actually looking for a table. So I'll go into images. I prefer a table that will show me all the necessary differences. So here's one that looks good. So I'll open up the web page and then we can zoom into the image and just detail some of the differences between these two. So I'm not sure what's going on. There we go. It's downloading. All right. So we just scroll through and search for the table. I hope the table is here. Very good. There it is. So here you can see in this table, it says an analog signal. First of all, the difference at the signal level, analog signals is continuous and it represents a physical measurement. What this statement is saying is the analog signal is infinite, means the values are infinite. So if I have a 20-volt system in an analog signal, how many frequencies do I have? The zero, between 0 to 20 volts is infinite because I can have 0, 1, 2, 3, 4, 5, and between 1 and 2, I can have 1.0001, 1.0002, and so on and so forth. So it's infinite. And it represents the actual measurement, means the signal contains the information, it contains the message. Whereas a digital signal is discrete. And discrete here means that it is modulated. That modulation is what we did. We said 5 volts to 5 to 10 volts, we use it to encode a 0. 15 to 20, we use it to encode a 1. That's the modulation process. So we restrict it to just a discrete set of values. So if I'm using discrete base 10 electricity, it means the value for the electricity will have 10 values. For binary, only 0 and 1. So the example I gave you is digital binary. I can have digital hexa, I can have digital decimal, I can have digital octal, and so on. The next says, what type of waves does it use? Analog signals use those sine waves. Those are those smooth, curvy sine waves. And the digital signals use square waves. So let's take a look at what sine waves look like and what square waves looks like. This is what they look like. You can see it in this image. And an analog signal uses a sine wave. So the sine wave is these smooth, curvy lines, whereas a digital signal uses these square waves. So the way you want to read these waves is a graph. On this graph, you just have 2 values, up or down, 0 or 1. So if it's not one thing, it's another. If it's not one thing, and the transition is immediate. But for the analog signal, any point on this line can give you a different value. And the number of representations in this are infinite. Moving on. The next difference is its representation. So we use continuous range of values to represent, whereas discrete, we use a discrete or fixed representation. Let me show you another example of this. So if we go up here and I search for, let's say, an analog versus digital clock, you will see the analog clock versus the digital clock. This is the difference. With the analog clock, which is what has the second hand here, the second hand is moving and it's pointing to the exact time precisely. So as the second hand is moving, it's going through an infinite set of values. So whilst the hand is moving between 0.1 and 0.2, it can be an infinite number of values. I can be 1.1000001, 1.100. So the analog system shows me the actual value as we traverse. Whereas a digital clock will show me an exact value. If I'm not 45, I'm 46. If I'm not 46, I'm 47. If I'm not 47, I'm 48. Discrete. Does that make sense to everybody? All right. So moving on. So that's the difference between the digital and the analog. Let's look at a couple of other differences and continue. So the example, human voice, air, any signal in the real world, every signal in the real world is an analog signal. So sound, electricity, radio waves, all are signals. Digital is a way of reading analog signals. So we can digitize light signals and have them in DVDs and CDs. We can digitize electricity just like we did by modulating it to 0 and 1 based on its voltage. So 5 to 10 volts will be 0 and 15 to 20 volts can be 1 and so on. Now, here's the more interesting thing. For data transmission, when we're using analog signals to transmit data, we can get a lot of noise. So a digital system is much better and much more immune to noise. So let's head back to the slides and carry on. So like we mentioned, the analog data is continuous and represents a continuous stream of data that can have an implication of the infinity problem. With a digital signal, on the other hand, we have discrete pieces of data. So if it's digital base 10, it's going to be 10 steps for the electrical current. So there will be 10 different notations. The example we saw was a binary value for a binary notation. So why do computers prefer digital signals? Long story short, it's simpler. It's easier to use. It's easier to do error correction. It's easier to compress the data, and it's easier to manipulate and handle the data. So why do computers use digital signals? Because they are easier to deal with. Why do computers specifically want to use binary digital signals? The reason is because binary digital signals are the simplest notation. So why use digital? Because it's simple. Why use binary digital? Because it's the simplest of the digital representations. It's just simple. So it's either an on or an off. So computers can work very well with this type of information. So when representing data in a computer, just like we have to learn how to speak a language, the computer also has to have a representation or a coding system. When I gave you an example, a sound file in a computer can be stored as a .mp3. An image file can be stored as a .jpg. And a text file can be stored as a .txt. These .txt, .jpg, and .mp3 are all encoding systems. I will show you an example of one encoding system, the ASCII system. Has anybody ever heard the term ASCII? American Standard Code for Information Interchange, ASCII. So this ASCII, I can Google the ASCII to binary table. And you will see in the notation how the computer stores characters in the sequence of zeros and ones. So I'm going to zoom in. So on this column, the ASCII column, you're seeing what is being represented, the data. Then there's the hexadecimal equivalent, the octal, and then the binary. So if you look here, we start with a bunch of special characters that may not make immediate sense to us. These are all special characters that the computer understands. When we slide over to the side, we begin to see characters that we're more familiar with. So you can start seeing characters of the keyboard, the $sign, the percent, and so on. So it means on your keyboard, if you type the $sign, the binary value that is stored is 001, 001, 00. So in order to store one single character, you need 1, 2, 3, 4, 5, 6, 7, 8 bits at least. So that means on my storage medium, if it's a magnetic disk, I need 8 magnetic dots. Each one, the polarity will inverse to represent the 0 or the 1, the 0 or the 1, the 0 or the 1. Am I making sense, people? So each character is 1 byte, and each byte is 8 bits. So if I have a file that is 3 megabytes, it means 3 million bytes. So 3 times a million times 8 will give me the number of dots on a magnet that I need to use to save that particular piece of data. So all of these characters you can see here now, I have the numbers. But be careful. Do you guys know the difference between a number string and a number integer? Quick question. Does everybody know? The difference between a number as a string and a number as an integer. An integer is a numerical value. And in binary systems, numerical 0 is 00000, 00000. 1 is 00001. 2 is 0010. 3 is 11. 4 is 101. So it just increments by 1. That's how you represent the integer equivalent for mathematical operations. The 1, 2, 3, 4, all the way to 9 you're seeing here is not the integer type. The ASCII table only encodes for characters. It does not encode for numbers. That means this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is not numeric, it's a string. In other words, I can't perform addition on these strings. I can only store them as a text in a text file. So it's just displaying as a string. If I wanted a number, the number is fixed. The notation of numerical operations is fixed. Then you can see a bunch of other special characters, and then you're going to see something strange. Here, you can see we have capital letters, capital alphabets, A, B, C, D, all the way to Z. But when we continue, we have the alphabets again, but in small letters. Because these zeros and ones are not representing the alphabets per se, they are representing the symbol that the alphabet represents. Does that make sense to everybody? So the character definition for capital A is 01000001, whereas for small letter A, when you type it, it's stored as 011000001. So anytime a computer wants to use characters, and it wants to represent characters, and maybe you type something on your keyboard, the computer's processor needs to identify the electrical signal of what you typed on your keyboard and encode it using a coding system like this one we're seeing called ASCII to represent the information. So many computers today don't actually use this ASCII notation. We stopped using this ASCII notation because of languages like Japanese and Mandarin. They have so many special kind of symbols and characters to draw. For example, the Mandarin, I think, has more than 2,000 symbols. English has just 26 symbols. Mandarin has up to 2,000 symbols. So because of we want computers to be compatible with different types of languages, the system that most computers use now is what we call Unicode. So this Unicode allows more bits to actually be stored. So we can actually look at the Unicode table, and it's an extensive map, but it's basically the same. The ASCII representation is very simple to understand. That's why I used it. It's not different from the Unicode. It's fundamentally the same concept. It's just that the sequence of zeros and ones are different. So the Unicode encompasses more characters. ASCII only has 8 bits. Unicode has more than 8 bits, which allows it to represent more things up to the 2,000 characters that we might need in the Mandarin for representing Mandarin symbols. So the next part of the slides is essentially Number conversion. How many bits make up a byte? 8 bits make up 1 byte. 4 bytes make up 1 word. And 2 words make up 1 long word. What's a word? In English language, I can spell a word by combining a bunch of characters. So for example, cat is a word, C-A-T. Dog is a word, D-O-G. So in a computer, when I'm building up blocks of data or blocks of information, I can use the zeros and ones in blocks of 8 to represent data values in the real world. So 8 bits is considered a byte, 4 bytes is considered a word, two words is considered a long word, and so on and so forth. It's not too important. It's just basically you want to know the larger that just like in English language, we can have a word, a sentence, a paragraph, a chapter, a section. So also in the collection of the zeros and ones inside a computer file, we can also segment them and define them as such. So when looking at computers, the higher the bit count, the greater the amount of data you can actually represent. So here I have an example of Super Mario. It's a game that is basically rendered on a computer. So the first Nintendo system that ran Mario was an 8-bit computer. Using the 8-bit system, this is the detail of graphics we were able to do from 1985 to 1991. You can see there were some improvements, but still the image is very flat. When we get to 1992, we move from an 8-bit system to a 16-bit system, so it has double the bit count. From the 16-bit system, we now moved on to Nintendo 64 in 1997, which was a 64-bit system. And you can see now the render is in 3D. It has more detail and more depth. So what does a bit count, how does a bit count affect the quality of data? It affects it, the more the bit count, the more the data. Let me give you an example. Let's say I asked you to write an essay of how you spent your last holiday. And I say limit your essay to 300 words. Versus if I told you write me the same essay, but you're now limited to 10,000 words. So if you write the essay with 300 words, there's only so much detail you can capture. You have to shorten everything because you only have 300 words. Whereas if you had 10,000 words, you can include extra detail to make the story more engaging, more interesting, and more detailed. That's the same thing that happens here. If a computer is an 8-bit computer, it's limited to 8-bit representations of data. If it's 64-bit, then it has up to 64 bits of data to actually deal with. So which means it will be more detailed and more defined. Does that make sense to everybody? Can I get a quick thumbs up? All right, good. So let's move on. So with the numbering systems, something about the history that you need to know. We have many different ways of representing numbers. Like I just showed you, the ASCII is a character representation. In the mathematic representation, we have different systems. So the first type we had was the stick figure. That's what the cavemen used to use. So they just used to scratch. So if you have 10 objects, you will scratch 10 times. Then we have the Roman numerals. If you remember how Roman numerals work, there's the I, triple I, then V, and so on to represent different characters. Then you have what we call the Arabic numerals, which is the modern day style that we're using. The history for the Arabic characters, that's basically the decimal numbers that we use today, the 1, 2, 3, 4, 5, 6, 7 that you're using now, is actually an Arab invention. The Arabs were the ones who first defined the number 0. Before that, normally character counting of data begins with 1. So you have 1, 2, 3, 4, and so on. The concept of the 0 was as a result of development in mathematics, particularly by Arab mathematicians, who then coined the system that we do algebra today. So there's a fellow called Al-Khawarizm. He's the father of algebra. So if we go to our web browser here and we Googled father of algebra, we will see Al-Khawarizm. So let's take a look if we can see what his face looks like. So this is the face. So if you don't like math, this is the picture of the face of the development of mathematics. So move on. Let's move on. So what we're discussing here is basically the different representation of number format. So you have binary, you have decimal, hexadecimal, octal, and so on that you can use for definition. Now, the reason why that algebra, the Al-Khawarizm Fellows work was so beautiful is because of the notation of positions. So it allowed us to do calculations much more effectively and efficiently. Can you imagine doing multiplication and the division using Roman numerals? Let's say you want to do 5 times 4. That's V multiplied by IV. You know, how do you begin to work it? It's crazy. So this notation, the decimal notation and the invention of the zero is what basically allowed us to pioneer mathematics. So everything here now you're familiar with. These are the number conversions. So you have examples of how to convert base 10 to base 2. You have examples of how to convert base 16 to base 10 and then down to base 2. And you have examples and so on. Last thing that we're going to look at is the calculation for what we call the range of values. When I mentioned that the bit count of a computer is important in how much data it can represent, this is the proof of the concept. So I'm going to switch over. Hold on. Let me find my Teams. There we go. I'm going to switch over to my whiteboard. Right. So this range of values, imagine, let's say I have a 2-bit computer. A 2-bit computer means all data is only stored in 2 digits, meaning the smallest representation I can have is 0, 0. After that, 0, 1, then 1, 0, then 1, 1. After that, I've run out of unique representations. So if I use this 0, 0 to represent item A, and I use 0, 1 to represent B, and I use 1, 1 to represent C, then I use, what the hell did I just do? 0, 0, 0, 1, 1, 0. So this is supposed to be 1, 0. There we go. So then here, I used to represent D. What will I use to represent E, F, and the rest? Nothing else is available because this is a 2-bit system. So the range of values of a 2-bit system is 1, 2, 3, 4. I can only have 4 characters represented in a 2-bit system. So that formula, R equals to B raised to power K, is what helps us calculate that. So what it says is R is defined as the range of value. That is what I'm looking for. How many representations can I have? B is the base that I'm using. In this case, typically base 2. Then K is the bit count, number of positions, bit count. And in this example, I have 2. So the range of values is given by base, which is 2, raised to power K, which is 2, which gives me 4. That is why there are 4 possible representations here. Does that make sense? So let's say I have a 3-bit system instead of 2. So here's a 3-bit computer. So this is a 3-bit system. The smallest number will be 0, 0, 0. Then I can have 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So if I count this, it will be 1, 2, 3, 4, 5, 6, 7, 8. So there will be 8 possible representations. And that is going to be given to me by my formula, R equals to B raised to power K. So what is B in this case? Binary values, base 2. What is K? 1, 2, 3. 3 positions. So 2 raised to power 3 is what? 8. So that is the point of that formula. So if you want to know how many bits an 8-bit computer can represent, how many values an 8-bit computer can represent. In other words, if you remember the ASCII that we just saw, American Code, Standard Code for Information Interchange, that table was an 8-bit representation, which means the ASCII can be used by an 8-bit computer. But because it's an 8-bit computer, the range of values is given by 2 raised to power 8, which gives us 256, which means I cannot represent anything more than 256. So on my keyboard, if I'm going to use it to represent character, my keyboard has to accommodate the 26 letters of the alphabet, but it has to accommodate 2 26s, one for uppercase letters and the other for lowercase letters. Am I making sense? Then you have your special characters, your special symbols, your dollar signs, right? Your special symbols, your dollar signs, your plus, your minus, your dash, your semicolon, your column, your period, all of that. Then you have some other special symbols that are control instructions and so on. Let me show you some examples of these special symbols. I'll switch over to my main computer. So if I open up, let's say, let me open up a random Word document. So I'll just go ahead and let's open up this. So in this random document, there's a special function that I have here that on my Microsoft Word, it can show me the special symbol. So you see this, where my icon is hovering. If I click on it, it will now show me the special symbols in this Word document. So if I zoom in, you can see some special little characters, some P's, some things that look like dots and whatnot. These are all hidden character information. Even your spaces are represented by characters. So the ASCII, when it's storing this file, if you want to store this file, for example, in ASCII format, every single symbol you use. So next line, new line, space, paragraph, period, all of this has to be documented. You can even see there's even a special character here that looks like a clock. So all of these have to be represented within that 256 range. So this is why when we started building computers that were compatible with Mandarin, we needed a larger representation. So we can't use 8-bit systems anymore. So we now use Unicode, which expands the functionality and the applicability and grants you the ability to be able to represent more symbols, and more symbols means more data that you can actually represent. So your modern day computer is actually a 64-bit system. So that 64-bit system also defines how much RAM your computer can actually use. If you're using a 32-bit computer, the maximum amount of RAM you can conveniently use is 4 gig of RAM. But if you're using a 64-bit machine, then you just do the range of values. 2 raised to power 64 will give you the amount of computer RAM that you can use and the amount of symbols or data you can actually represent inside that system. The rest of this is just showing us our different base numbers and showing us how to do the conversions. So from base 8 to hexadecimal, and then how to do basic addition, subtraction, manipulation, and so on. And that's that basically. So the rest are just mathematical examples of how to convert. And we're done. So are there any quick questions? If you need to practice and remember how to do the number conversions, there are lots of YouTube videos that can give you a refresher. Will those number conversions be coming out in the exam? Not really. I don't like asking those questions because they're too simple and straightforward. So typically I will discuss the theory and I will ask questions related to the theory. But you still need to know basic number conversion so that you can understand how computers manipulate data in the system. So when we enter the topic of logic gates, which we will spend about 2 or 3 weeks on, we will delve deeper into these concepts. So we will better understand how computers can actually do the manipulation part of data. So if everything is clear, can I see a thumbs up? Everything so far, the fundamentals is clear. So to do a quick recap, we basically saw how computers stored information, and we said that computers store information in electrical signals, but those electrical signals have to be represented by digital signals, and those digital signals are transcribed into digital bits, which are zeros and ones. So computers use binary digital systems because they are the simplest form of the implementation of digital signals. It's easy to compress, easy to do error handling, and it is easy to manage and manipulate by a computer. We saw the differences between analog and digital signals. We then looked at how computers were able to store data using different technologies, the magnetic, the optic, and we said in the next class, we're going to look at the electric when we look at the logic gates and so on. And that's the story so far. So don't forget, you have the assignment of looking at this data representation PDF document that I shared. It will give you some better rounded off understanding. So try to look at it before the next class. So I'll go ahead and stop the recording. For those of you that still have attendance issues, you can then we can then deal with the attendance. So let me share my screen here real quick. Oh, sorry. Let me stop the recording first.